Go ahead.
Okay, so, I mean, the stuff I do is not really connected at all with the topic of the conference, except that there's some connection with modular forms. I can say something about how modular forms appear in something related to what I work with, and I just sort of want to push on that connection a bit, and just give some evidence to the maximum that Zagier always says, that modular forms are everywhere. So the thing I work with is called multiple zeta values. And the idea goes back to wanting to investigate, in some sense, the Riemann zeta function, or rather special values of it. So the Riemann zeta function is this sum over all positive integers, 1 over n to the s, convergent for s greater than 1 in the real part. And you can ask about special values of this thing, such as, so for example, it was shown after quite a lot of work by the lecture by Euler that zeta 2 evaluates to pi squared over 6. And similarly, he evaluated zeta of 4 and zeta of 6 and all the even zetas to be appropriate powers of pi. And that's a really bad typo. That should be zeta to the 6 over 945. That's definitely not pi to the 9. And so more generally, all of the even zetas are some power of pi or some rational multiple. And already you see maybe there's some connection with the modular form side of things, because this was the coefficient that was appearing in the Eisenstein series. And so maybe we can make some connection here and get something interesting out. What I want to look at, sort of first of all, is we can see that the even values of zeta are quite nice. They're rational multiples of pi. We can ask a similar question about the odd values, and we really have no idea what goes on there. So zeta of 3, sum of 1 over n cubed, you can evaluate it numerically, you can do some experiments, but you can see very quickly that it doesn't seem to be pi cubed times some nice rational. So that's kind of surprising given the previous formulas, but that's what it is. What has been shown, though, is that zeta 3 is irrational. So if I go back to the previous slide, we have zeta 2 is pi squared over 6. Well, it's well known pi is irrational. It's well known it's even transcendental. So zeta 2 is definitely irrational, and very much irrational. So zeta 3 has been shown to be irrational, but that was only very, very recently, in the end of the 70s. And this was already a huge breakthrough. You can then ask the same question about zeta of 5, but we know literally nothing about that. We can't prove that it's irrational. We expect it's irrational, but we can't say anything more than that. The best we can do is to say something like 1 of zeta 5, 7, 9, and 11 is irrational, at least one of them. I mean, we expect them all to be irrational. That's the thing. They should all be irrational, but we can only prove that at least one of them is. And the idea there is you can show something about the dimension of the vector space they span if you look at more and more odd zetas, and eventually you get some value that has dimension greater than 1. So at least one of them has to be irrational. And then some work can let you get a particular range there. But for like a surprisingly simple function, at least in terms of how you write it down, 1 over sum of n to 1 over n to the s, you very quickly run into questions that are impossible to answer so far. So maybe the idea is we want to do some work to understand the zeta function, the values of the zeta function. Maybe we can fit it into some bigger algebraic structure, have some more properties we can play with, and we might be able to make some progress. And that's, in some sense, one of the motivations for introducing multiple zeta values. So you just make some fairly obvious multivariable generalization. Now, the fairly obvious one would maybe be to have all of these sums running from 1 to infinity, n2 is 1 to infinity, so n1 is 1 to infinity, n2 is 1 to infinity, n3 is 1 to infinity, and so on. But that's just going to be the product of zeta k1 times zeta k2 times zeta k3, so it's not really anything new. You put the inequalities in and you get something that's a bit more interesting. And for convergence reasons, you want to take dk to be greater than 1. Sorry, that's another typo. That should be kd, not dk. But then there's a couple of properties you want to define about this thing. The weight is the sum of the arguments you're evaluating, and the depth is the number of them. It's just some nice terminology to refer to things with. And so the motivation for this is by looking at the product of zeta of A times zeta of B. We can expand it out and decompose it into these pieces. And so somehow we've already got a bit of a better algebraic structure.
Yeah, because if you knew that the zeta of one value is algebraic in the zeta of another value, it would be you can hope that you get some phi or something nice, right?
I mean, sort of, yeah. It's just having a bigger space where you can take products and do things, and where you find more interesting relations between things. You can possibly pull it all back down and figure out something about the value of the individual zetas, you know, the depth one, Riemann zeta things. So it's just an aid of having some bigger space where you have more freedom and more structure to play around with. So you might just write this down as some random thing to play with as a pure mathematician. But surprisingly, once you've introduced this and you start doing calculations with it, you find it appearing in lots of random different places. So for example, it appears in not invariants. There are certain not invariants that are computed as iterated integrals of some form, and they turn out to evaluate to multiple zeta values or related objects. The second place they appear, and this is a shout out, I guess, to Danilo, is that Dirichlet eigenvalues of regular polygons turn out to involve multiple zeta values. You can show some behavior on those. Danilo has a paper out a year or two ago with some collaborators where they do some computations and prove some things there.
So you mean in a polygon, I do the Laplacian and something like that?
I think it's something like that. I'm not so familiar with the actual results of that paper, but yeah, it's along those lines. They also make appearances in high energy physics. So, you know, all of these experiments at CERN where they're colliding particles together, the sort of calculations you do to understand the behavior of that, involving drawing these, these diagrams where you have a particle coming in, maybe turns into a photon, turns into a pair of photons, does something. I'm drawing nonsense here, recombines, and then pops out again. You want to be able to evaluate like the chance of that happening and some overall possibilities. Well, those sort of calculations end up involving iterated integrals of certain forms, and they quite often turn out to be multiple zeta values or multiple polylogs. So, you know, this stuff does get used quite a lot in the physics area. And then really, just as the last thing, it appears in number theory in some sense. Like I'm studying these objects really from a number theoretic point of view. So the applications are secondary to me. Just the actual structure and relations and properties on their own is interesting enough for me. So let's have a look a little bit more at these algebraic properties of the things. Well, the first surprise is after you've defined this multivariable version of the zeta function and look at special values, you get an astounding number of relations. So in principle, you might think that initially, if you look at something where the sum of the indices is 10, that you'd have 2 to the 8 different possibilities there. If you just write down all the choices like 1, 1, 1, 1, 1, 2, 1, 1, 1, you know, 1, 1, 1, 1, 3, 1, 1, 1, 2, 2, and so on. You get a huge number of possibilities. But when you do the numerical computations and see how they're all related, there are very, very few independent ones. So there are lots of relations. And I've just got a little scattering of relations here. Just a little selection. There's plenty more of much more complicated structure, etc. But the relation up in the top left here is the simplest example of something called duality. And for the longest time, it was really surprising how such a thing worked. There seemed to be pairs of MZVs that evaluated to the same thing, and nobody could explain it until a little bit of insight about rewriting them in a certain way made it completely obvious. Then you have something down here where you're summing up all of the choices, ijk equal to n. And when you sum them all up, you get just the original Riemann zeta value. And this sort of thing generalizes. It's an example of something called sum formula. The one down here involving weight 12 zetas and some really weird looking coefficients is actually the example, is sort of the motivating example, the key one that I want to get around to at the end of the talk. This thing, surprisingly, comes from the fact that this discriminant function, the delta function, this weight 12 cusp form exists. It directly implies that this relation is true. So yeah, as I was saying, if you count up the number of actually seemingly independent, linearly independent MZVs of particular weights, you get very, very small results. So as I said, in weight 10, where you would expect 2 to the 8, so 64 different things, there turns out to only be 7. And it's really a very slowly growing sequence. And I should say up front that we can't prove that these upper bounds are correct. We don't even know, as I said, we don't even know that zeta of 5 is irrational. So we can't even show that the weight 5 space here is more than one-dimensional. But there's all sorts of big and fancy conjectures that put these dimensions into larger setting. I should probably throw around words like mixtape motives and whatever, but that's just fancy nonsense. These are known actually to be an upper bound. There is definitely fewer, less than or equal to this many, but we can't prove that there's even more than one in a particular weight. In fact, we can't even prove, in some sense, we don't know that zeta 5 is irrational. So theoretically, this weight 5 thing could collapse down to the empty set because it would be a rational number and so really weight 0. So this is just an upper bound, and we have no idea if it's true or how close to being true it is. But you can play around and see that there's some structure here. In fact, the dimension counts seem to satisfy this recurrence. I guess if you check, weight 9 has dimension 5, weight 10 has dimension 7, and they add up to 12. And this pattern seems to continue. I have no idea if it's actually true, but it's provably the upper bound. So, okay, let's.
So the upper bounds satisfy this with an inequality? The upper bounds are sublinear or super.
Well, I mean, conjecturally, this upper bound is actually the right dimension, and so should satisfy this exactly. If something happened to collapse down for whatever strange reason, I don't know what that would say about the dimensions of higher ones, whether you could make some argument that you could take something in lower weight and sort of lift it up somehow. But it would certainly be a strange implication in any case. So, you know, as I gave us some sort of motivation for introducing the multi-zeta things, it comes from wanting to be able to take products and get this nicer algebraic structure. And so, of course, once you've introduced the multiple value versions, you can look at how the product works in general. And in one case, we can expand out product of series just in a fairly obvious way. You say you want to take just all ways of making these indices compatible. So I has to be less than j, but k could fit in, between 0 and I, between I and j, after j, or it could be equal to I, or it could be equal to j. And you just generate all the possible terms like that. And this sort of pattern for making the product works in general. So you get relations like zeta of AB times zeta of C is this linear combination of things. And there's a fancy formal way of encoding it that's basically just trying to capture the idea that when you multiply zeta of A, is it some zeta times another zeta, you either want to make the index corresponding to the sort of first argument either first, either come before the index corresponding to the second argument. So you put it here. You want to make the second argument, the index corresponding to the second argument come first, or you want to stuff them into the same slot. So it's this inserting k either before I, after I, or equal to I, and then just building it up like that. And this is encoding the product by representing the zeta value n1, n2, blah, 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 as a word in z of n1, z of nd. So this gives us one nice algebraic structure. But surprisingly, there's a completely different way of rewriting these things. That's using
Later there will be a question about slide 9, but
Yeah.
maybe.
Sure, yeah, if you have questions, I can take it at the end. But yeah, there's a completely different way of rewriting these things, and that's as an iterated integral. Spotting more typos. The differential forms here should be dt1 over t1 minus x1 and dtn over tn minus xn. But it sometimes gets a bit tedious to write all of the indices, so one gets a bit sloppy. So the idea is we can write zeta of n1 comma comma nd as an iterated integral where we take the forms dt over t minus 1 followed by a number of dt over t's, however many corresponding to n1 minus 1 here. And we stick another dt over t minus 1 and then dt over t repeated so many times. And it's fairly straightforward to prove this, at least in a special case. And you can see the argument generalizes. It's just expand out the dt over 1 minus t as a geometric series, do the integration, and repeat the process. So you do it for the case of dt over 1 minus t, dt over t2. Do first integral, do the second integral, and you get exactly the series definition. And it's the same pattern in general. And this is the representation I mentioned a few minutes ago that makes it completely obvious that two completely different MZVs should be equal. So you take one, write it as an integral, apply the change of variables t goes to 1 minus t, and that has the effect of reversing the path you're integrating over. So reversing the t1 less than t2 less than to be the other way around, and switching over the forms dt over t minus 1 and dt over t. So you can formally just write it down as a string of ones and zeros, and then change the zeros to ones and reverse everything, and then reinterpret that as another MZV. So to go back to the one that was on the slide a moment ago, zeta 1, 2 would correspond to 1, 1, 0. And you change that to reading from this side. Well, 0 goes to 1, 1 goes to 0, 1 goes to 0, and then that corresponds to zeta of 3. That gives you immediately that the two things have to be equal. But from this integral representation, you also get surprisingly a completely different way of multiplying the things. So we had a couple of slides ago this way of taking the two series and just interleaving the indices. We can do something for the integrals as well in more or less the same way. You just write down two integrals corresponding to MZVs, and then we can ask how the different indices can interleave and give something that's compatible. So we can either have S1 being less than T1, being greater than T1, and if it's equal to T1, then it doesn't contribute because it's an integral of like dimension 1 less than is interesting. It's something of measure 0, so it doesn't contribute. And I've just written down all of the indices. So you can then sort of rearrange everything so that the things are labeled in the order that corresponds to the differential forms and get something a bit nicer. So if you do that multiplication and expand everything out, you'll see that that product is then 4 times zeta of 1, 3, and plus 2 times zeta of 2, 2. Again, just reading off the forms here. So you get a 1 followed by a 3 from this string of integrals. Then you get a 2 followed by a 2 from the other integrals. And gives you and again, you can encode this more formally as some algebra structure where you either take the form corresponding to like the first letter and put it in front or behind the one from the second word. But again, it's just a fancy way of encoding this. And the idea from the first few equations on the slide is the really key thing. But now this means we have two completely different, well, I don't want to say incompatible, they are compatible, two completely distinct ways of multiplying these things. So what should we do? We should see how they compare and see what that tells us. So for example, from the two calculations on the earlier slides, we have one way around the zeta of 2 times zeta of 2 is with this series multiplication. It's equal to 2 times zeta 2 comma 2 plus zeta of 4. Then from the previous slide, we've got this way of multiplying the integrals. And so because the sort of main term, the 2 zeta 2,2 bit cancels, you'll get a relation that says zeta of 4 is equal to 4 times zeta of 1, 3. And so this gives us some source for the relations that are appearing on MZVs. The fact that there were so many seems like it might be coming from this way of comparing two completely different product structures. And the idea is somehow, yes, that's really what we expect. And I have to take a bit of care because you definitely can't get all relations from this naive approach. For example, there will be no way to get kind of this relation zeta of 1, 3 equals zeta of 1, 2 equals zeta of 3 from that, because you don't have anything in weight 1 that you could multiply by a weight 2 thing. This zeta of 1 doesn't exist. It's, you know, go off to infinity. But you can sort of get around this and formally allow something like zeta of 1 and give some, you know, and there's some notion of regularization which will let you make sense of this thing. And so if you do that extension, then yes, one of the main conjectures in this area is that all the relations on MZVs should come from this sort of compare one product structure with compare the other product structure. And of course, this is completely impossible to prove at the moment, because it would immediately have the very simple consequence that zeta of 5 is irrational. Just for the simple reason that, you know, if all relations followed from this, then all relations would have to be homogeneous in the weight. You can see from doing the product that on this side we have something of weight 2 times weight 2. We get something of weight 4 over here. Taking the other product, we also get something of weight 4. So the only relations would be some linear combination of weight whatever equals some other linear combination of weight whatever. And that means we would prove that the zeta of 5, which has weight 5, can't reduce to a rational, which has weight 0. But yeah, since we can't do that, this is impossible to prove as well. And that's more or less what I just said is we need to include the regularization to get this weight 3 identity, and trying to prove any relations just with this direct comparison is really, really tricky. You just have to set up a big linear algebra problem or find some nice structure. But it gives us some hope that there's some understanding and structure going on there. So now, I just want to quickly write down what it looks like for products of 2 zetas. You can write this very explicitly and get that zeta of A times zeta of B is one way around from the Stuffle product, multiplying the series, and another way around gives you this combination from the Shuffle product. And with this slide, the only point I want to make is that there's a way we can encode this via some generating series and get some connection to like relations between polynomials with certain choices for coefficients. That's just something that I'll come back to in a few slides' time when I make the connection to modular forms. So just bear that in mind. There's some way of encoding this as like relations between polynomials. So now I want to go on to the modular forms relations. And for that point, let's go what I mentioned like way back at the start. These Eisenstein series have as their constant coefficient zeta of k. So if you have a relation between Eisenstein series, then by taking the constant term, you're definitely going to get a relation between zeta values, or like products of zetas are equal to some other zeta. So that's one sort of source of modular form relations, but it's not really the interesting one. I want to claim there's a more interesting set of relations coming from particularly the cusp forms. And so in order to make that precise, we need to actually introduce some notions that Daniel talked about in his lecture. In fact, is associated to any cusp form, or at least any cusp form in SL2Z, it probably works more generally. You can look at the period polynomial. So this was taking like this Eichler integral, looking at how nearly modular it is. The sort of remainder term gave you some polynomial contribution. Or you can write down a very explicit formula that says the period polynomial is some polynomial, some homogeneous polynomial with these coefficients Rn of f, which are given by very explicit integrals. And again, I don't think Daniel actually mentioned this, but a fact we have is that up to a single transcendental number, the even part of this polynomial, so the x to the even, y to the even bit, has rational coefficients. They're all the same transcendental thing times a rational. And there's a different transcendental thing that fits into the odd part. So really we can view this polynomial as a polynomial with rational coefficients if we rescale everything. And if we went back to the start and took our cusp form and divided it by this transcendental number, then the result would be rational things in the end.
Not as explicit for
I mean, well, you could compute it. So, I mean, you could compute it as just take any one of these periods, take R1, compute that, and it's the thing. If you divide by, you'd make everything else rational. As an example, I don't know if you could compute it as any particularly nice number other than just it's this integral and numerically it's something point blah blah blah. But it's a kind of deep fact that there is such a transcendental number you can use to get rid of all the transcendental bits. And then this is roughly what Daniela was hinting at, and I'm again stating it in a very, very vague way here. But somehow these period polynomials are essentially isomorphic to the cusp forms. So the properties of the period polynomials, however, you construct the period polynomial, see what it behaves like, that's telling you something about the cusp forms. And actually, point I want to make here is the period polynomials are going to have very special properties. In particular, the fact you can take the integral from 0 to I infinity and add the integral from I infinity to 0 and it'll cancel out to 0, or the fact you can go around some closed loop from 0 to I infinity to 1 to 0 means that when you make certain changes of variables in the period polynomials, you have to get 0. And this is just these two relations down here, that p plus p slash with s is equal to 0, where this slash operator is kind of fairly closely obviously related to the thing for modular forms as well. We have some automorphic factor and some change of variables. So the period polynomials have a special sort of structure. And that actually means that and these relations are essentially sufficient to write down any period polynomial. You can therefore just take polynomials of the coefficients, find the ones that satisfy these relations, and they will be the period polynomials up to some slight hand waving. There's lots of details I'm missing out here. But once you've got those, they are essentially isomorphic to the behavior of the cusp forms. So I just want to go back to this notion that there was some way of viewing the double shuffle relations for the double zeta values as identities between polynomials. And there's some way to sort of construct general solutions to these relations via essentially an arbitrary polynomial that has certain properties. I think I want that it's even with respect to y. So if I change y to minus y, I don't change the polynomial. And I mean, there's a lot of technical details and extra work that needs to be done here, but roughly you can maybe see there's some way of building a bridge from this to the period polynomials. In particular, there's a theorem that says, and if you take any cusp form and look at the even part of the period polynomial, and you define some numbers, these AR justify the property that we want the AR to be the coefficients when we make this change of variables in the period polynomial, then I can automatically lift this to a relation between double zeta values just by taking this coefficient, multiplying by r factorial, weight minus r factorial, and plugging in the zetas and making the arguments 1 bigger. And so directly from the cusp forms, you get double zeta relations, which is initially really quite surprising. And just as like 2 examples, just to give you some idea that these things are very, very explicit. In weight 12, so in degree 10, so the period polynomial has degree 2 less than the weight we're considering. You can set up the linear algebra and see that this is the only period polynomial. And the recipe from both 4 says we ignore the odd powers because we're summing over r being even. We take all of the terms remaining, multiply by the powers of the factorials of the powers. So here the minus 28 times blah, 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 goes to minus 28 times 4 factorial, 6 factorial. And then we increment the powers as the arguments of the zetas. When we do this for all the terms, the claim of this previous theorem is it should be some rational multiple of zeta 12, and it indeed is. I mean, explicitly on the slide here is the multiple you get. And I've written it in this way so that you can actually cancel 4 factorial times 5 factorial from everywhere and simplify it down, and you will get the relation I had on one of the earlier slides. So you get this rather suspicious looking number over 691s, the denominator or numerator with a Bernoulli number. And this sort of thing happens also in weight 16, where there's another cusp form. So in weight 12, we have the delta. In weight 16, we have delta times, I guess, delta times E4. But in weight 14, there's no cusp forms. The dimension says that it has dimension 1, and that's the Eisenstein series. And so there's no relation in weight 16 for the, in weight 14 for the MZVs. In weight 16, you have another cusp form. You can construct a similar relation with very explicit rationals, and you get this surprising connection to modular forms. And actually, maybe it's worth saying that this connection and the fact these relations exist really broke one of the early conjectures in terms of what might be a nice basis for MZVs. Somebody had the idea that you could maybe take zeta of odd as like a basis for the depth 2 bit, and then construct something similar for depth 3 and so on. But the fact you have this linear dependence already in weight 12 means that that idea just had to be completely scrapped. The other surprising thing is these modular form relations keep cropping up again and again as you have more and more relations for MZVs cropping up in higher depth. So somehow you can write, say, zeta of 222, 4, 222 in terms of depth 2 things, and you can in fact conjure it up in such a way that you can get a single zeta odd as a sum of zeta 222, 4, 222s. And so whatever the modular form relations you have for the double zetas you had there initially, they have to propagate to these more complicated ones. And this behavior just keeps infiltrating all of the higher depth MZVs. But the fact that there is a connection to cusp forms is initially really quite surprising. I mean, that's broadly all I wanted to say on the topic. Just to give you a bit of a flavor of a slightly different area that still has a connection with modular forms.
So there was a question in the chat.
Should I go back to slide 9? Okay, but broadly, I'm being sort of deliberately vague here. I mean, I don't really want to say anything about how you're actually doing anything with the numerical side of things. So how do you make sure that LLL gives a good minimal guess for the dimension? I mean, somehow there's just some numerical experiments that you can start writing down, say, zetas up to, all the zetas up to a certain weight, and start trying to find short relations between them by running LinDep on a small subset. Okay, granted, when you start going to something like weight 12, where you have already 1,024 possibilities, you need to go to really high precision if you want to tackle the entire set of things. But you can maybe start with some sort of small candidate set, see if there's any relations there, and then start adding 1 or 2 terms and trying to reduce to what you've already considered, and just sort of step by step eliminate things. I don't know if that answers the question particularly well, but
I think it's it's hard to answer more precisely. Okay. More question? Yeah.
This might have been covered earlier on, but so where the inputs for these are the powers that you're taking, right?
yeah.
Has much of any work been done for non-integer inputs?
I mean, there is more generally a notion of a multiple zeta function where you can take K1, K2, to be arbitrarily complex numbers. but somehow already the multiple zeta functions are nowhere near as nicely behaved as the Riemann zeta function, in the sense that the Riemann zeta function has this functional equation that lets you go from positive s to negative s and get results like that. I think for the multiple zeta functions, you end up getting really weird behavior where there are like infinitely many singularities on certain hyperplanes, so there can't be any functional equation like that. It's more like they sort of cluster along a diagonal or something. So people have certainly studied multiple zeta functions, and so arbitrary powers or arbitrary powers here. But they're definitely not as nicely behaved as just the values. In fact, you already run into issues like the fact that taking limits in different directions gives you different results. So I think this is also connected to some of the ideas of regularization, that you can write the sort of regularization coming from the sum and the one from the integral as a sort of limit in terms of how the arguments are going to zero, either holding them constant as say 1, like 1, 1, 1 epsilon, or holding them as epsilon, epsilon, epsilon as epsilon goes to 0. And you get really wildly different behavior. So yeah, people have studied them. They're definitely not as nice, but people are still continuing to study them.
Okay. So thank you very much. There is something more in the chat, but